Hello, today, in continuation of the topic of quantum numbers, we will learn to do practical tasks, exercises that are related to these numbers. So the first task I propose to do is as follows. For the element nitrogen, which has the number 7, and we'll take its isotope with a mass of 14, we'll write down the quantum numbers for its electrons, and it has 7 electrons. These electrons are placed in the bohr. The first level has 2 electrons, the second level has 5 electrons. The electron shape would look like this: 1c2, 2c2, and 2p3. If we place this by quantum cells, it looks like this. C2. We'll have electrons. 2 in a quantum cell, they're called paired. Then at the second energy level, we have a C2, and they're paired. And in the second energy level, we have 3p electrons, which have unpaired electrons. So now let's write out a set of quantum numbers for each of these electrons. So this is the first electron. This is the second. The third, the fourth, fifth, sixth, and seventh. Let's put these numbers here. First electron, second, third, fourth, fifth, sixth, and seventh. So this is where we have our electrons. Nitrogen has 7 of them. Let's give the quantum numbers for each of these electrons. The main quantum number, as we can see, is this. There's one here. This is a C electron, so the orbital number is 0. The magnetic number in this case 0, because plus or minus L and the spin number, since the electron is up, plus 1, 2. The second electron, which is placed down, is an electron that has a quantum number, main quantum number 1, orbital number 0, magnetic number 0, but it is placed down, so minus 1 second. Next, the third electron. This is the second energy level. It is also C electron 0, magnetic number 0, and it is also located upwards, plus 1 second. Then electron 4, also second, orbital number 0, magnetic number 0, but it is positioned down, minus 1 second. These electrons that are number 5, 6, and 7. The prime number is 2, but these are p electrons. So 1, in which case the electron at number 5 is minus 1, so it's plus 1, 2. The sixth electron also has a level 2. Also has an orbital number of 1, but this cell corresponds to the magnetic number 0. And it's also upwards, so it's plus 1, 2. The seventh electron, also in the second level, orbital number 1, but it is located in the outermost cell. This corresponds to plus 1, and also has plus 1 second. And once again, let's make sure that the Pauli principle works. Pauli's principle, which says no 2 electrons, for example, can have the same all quantum numbers. Note, even electrons located in one quantum cell, let's say one with, they differ in spin number. Well, for example, the fourth, fifth electron differs respectively. We have an orbital number, and in this case, spin numbers too. So, how to work in this case with quantum numbers, I hope it's clear. Now let's try to do the following task. So, for example, we've got an electron which is arranged in the following entry. Well, for example, we are talking about 2 electrons arbitrarily chosen by me. For example, one is located here and the second one is located here. Let's describe for each of these electrons a set of quantum numbers. So n for this electron, as we can see, is 3. N for the second electron is also 3 because they're in the third energy level. The number of cells is 3, so these are p electrons. The orbital number of p electrons is 1, so in this case they also have the same number. So ml for this electron that is in the first cell is -1, and ml of the electron that is here corresponds to +1. Already with this number, as we can see, they differ. And the spin number for this electron corresponds to +1, 2. It's moving upwards. And the spin number of the second electron is -1, 2. It is not difficult to see that in this case our arbitrarily chosen electrons differ in numbers, which are magnetic and spin. I hope it's clear. Now let's do the task in reverse. Let's depict in quantum cells in cells an electron that has the following coordinates. Let's say that the principal quantum number of some electron is 4. Let the orbital number in this case be 2. Let μ for this electron be 0. And let the ms of this electron be -1, 2. Let's place such an electron, find its position. So n equals 4, so it's the fourth energy level. L equal to 2, it corresponds to d electrons, so then the number of quantum cells is 5. And place an electron. So here we have -2, -1, 0. E +1 +2, and then where our electron is located here, and since its number is -1 second spin, it looks like this. So that's where this electron is. Let's do another one of these electrons in the same way. Let's have an, in this case, be 5. The orbital number will be 3. ml will be equal to, let it be -1. And ms for this electron, let ms be 1, 2. So mn equals 5, so it's the fifth energy level. L is equal to 3, so it is the f electron. Then we've got 7 quantum cells. So where -1 is, that would be -3, -2, -1, 0. +1, +2, +3. So that's -1. That's the quantum cell, and that's where the electron is located. So this task, I hope, is clear, and how to work with quantum numbers, I think, is clear. So look, we have done this task, so very often they ask in exams, for example, write down a set of quantum numbers, let's say, for the element nitrogen, phosphorus, and so on. So we have shown how to do it in this task, but there are also tasks when selectively asked for any electrons to reflect all quantum numbers and accordingly to represent them, say, in quantum cells. So I hope you understand how quantum numbers work in chemistry, and you will definitely succeed in such tasks. Goodbye.